Well, the subject of shear is a bit of a mystery for students in statics because it's not used in any other equilibrium situations. It's kind of an introduction to the concept that will get explored in more depth in mechanics of materials and other courses. But what's going on is that there are forces on the inside of most components and most beams. And here's maybe an easier one to look at. Let's say we have a bracket attached to a column here, and we're pulling on it. And you could expect that if I'm pulling this way, the column, this support here is pulling backwards on it. And what it's doing is it's putting some significant stresses on this bolt that's pulling it through, and those forces which cause stress, which we're not really going to talk about stress in this course, but those forces tend to happen at a sharp point, kind of at a line. Now you've seen shear happen when you cut a piece of paper with a pair of scissors or a pair of shears. That's why they're called shears. It's because they use shear to destroy or to make something fail catastrophically. When you're cutting a big bolt like this, sometimes you make it fail, break in half, and sometimes you just make it you displace the metal, and so that here is a complete failure, but hasn't actually severed and broken in half. But you can see what this bolt has done is it is kind of displaced from its neutral position. So clearly it's a failure in the bolt. And so we do see a bolt or screw or pin situations all the time where you have a pair of pliers or maybe you have a beam here, and all three of those pins might have some significant shear forces to be analyzed, and also beams. It may be a little bit harder to see a beam undergoing shear, but guaranteed there is some shear force that has some, maybe small, but it has some tendency to try to displace that beam in a vertical fashion like that. Clearly there's a bending that happens, and it's easier to see bending because you can observe that a little easier than you can shear. But both bending and shear cause stress inside beams and other kinds of hardware. Well, here's another example, I suppose, of shear in action, shear and moment in action. But let's say that you had a piece of metal that was bent in a semicircle like that. If you pulled on it from one side, you'd have to pull on it from the other side, and clearly you're kind of stretching it out, and you can see that it probably is experiencing some forces that could be analyzed. Or you can maybe do it the opposite direction. Take a ruler, like a plastic ruler or something like that, and you can shove it from both sides, pushing it in instead of pulling it, and you can bend it into a shape that looks like that. And I'm sure you've done something like this. If you push too hard, it will break it, and clearly breaking things is, in our engineering experience, is generally not what our expectation or what our desire is. We're supposed to be, as engineers, designing things that don't break instead of things that do. Of course, we will have to test things along the way. Now, just as a problem-solving technique, what we'll talk about in the next video, I believe, is discontinuities that happen in shear, in both shear and moment, but they happen where a force may be applied or where a reaction might occur. So what we'll say is that for now, the book will tell you that determine the internal force and shear acting at a point D, which is located just to the right of the support. In other words, if you try to define the shear right at the support, you basically get two answers, and one of them is would be if you're approaching it from this side. Another one would have it if you're approaching it from that side. So it's discontinuous. It doesn't have a single answer for shear. So what we'll do is we will define the shear that we're looking for either on the left-hand side of the support or the right-hand side. So very, very small distance there. Well, I want to just walk through this problem with you a little bit. This is a type of support that we haven't used before. It's called a moment release, and basically we have a fixed support beam, a cantilever beam right here, but it has a reaction over here with some loads, or it has a support over here with some loads, and in the middle we have something called a moment release. And basically it's just a hinge. And a hinge is able to accept force in the X and in the Y, but not moment. In other words, it's free to bend about that point. And what that does is it allows a beam to be supported, a fixed support beam to be supported out here. There's certainly other uses, but what we need to do in order to solve for the reactions here and here is you have to break it apart. There's no good way, no other way of solving for those reactions, even though you know the supports, because you have to break it apart into two pieces. And that's basically the using the frames technique or method of sections technique, where you separate one side with another side, transfer the mating forces equal opposite, and then you can find out what that moment reaction is over here and find out what the X and Y forces at A and B and C are. So I'll let you look at that solution. You can pause the video if you want to just kind of walk through, but the main thing is that there's no moment at the pin here, at that hinge, and that is the only way to be able to solve for those reactions. But once we solve for the reactions, then we need to solve for the load, or sorry, for the shear and moment at these points. And so it says, what is the shear and moment at D and at E? All right, so over here in D, this is kind of conventional, or what we've done before. Draw the section here, write the positive shear, positive moment, solve for the shear and moment like we have already done. Over here at E, I just want to point out that E is located, what it says is point E is located just to the right of the load. In other words, the load is on this side and E is on that side. So if I were to draw the section here of EC, because the load is because E is just to the right of the load, my free body diagram doesn't include that 3 kip force. It only includes the reaction, the C reaction, and then the shear in the moment. It doesn't include that 3 kip because that is basically out here in space compared to where I'm at. Anyway, that's the technique I just wanted to make sure that you understand. Do not include the force here, because then basically you'd be looking at the shear and moment on the right side of the 3 kip force if you did that. And again, you can walk through my analysis and make sure that you understand it. It's like that.